All right, I want to take an introductory look at polynomials, mainly looking at vocabulary, what is a polynomial, but also looking at a little bit of the math that we're first going to learn with polynomials. So polynomial, which means something like many terms, is a sum or difference of one or more monomials. So in order to define a polynomial, we have to look at these smaller things, monomials. A monomial is a product of a real constant or coefficient and a whole number power of a variable or multiple variables. So it's a product, which means they're being multiplied together. Whole numbers means 0, 1, 2, 3, and so forth. And the constants and coefficients have to be real. So these are some examples and non-examples of monomials. Things that are monomials. 8x to the fourth. 8 is most certainly real. X to the fourth, that's certainly a whole number power of x. If I say negative 2 is just a constant by itself, that's fine. If you also think about it, negative 2 can also be thought of as negative 2 times x to the 0. Anything to the 0 power, we remember, is 1. 1/3 x to the 10th. Again, 1/3 is real. X to the 10th, that is a whole power of x. And one last example, the square root of 10, x to the 3rd. 3, most definitely a whole number. The square root of 10 is real. It can only be approximated. It is irrational, but it is real. Things that are definitely not polynomials, or excuse me, not monomials, and thus not polynomials. The square root of negative 9x squared. Well, what's wrong with the square root of negative 9? The square root of negative 9 is 3i. We just said our constants and coefficients have to be real. X to the negative 3rd. Negative 3 is not a whole number. Whole numbers are 0, 1, 2, 3. They don't include negatives. Similarly, 0.4 is not a whole number. And lastly, another non-example, the absolute value of 5x. This wasn't maybe as expressly addressed up above, but the absolute value is itself something other than a whole power of a variable. I can't have things like absolute value. I can't have x inside an absolute value. I can't have absolute 5x or absolute x plus 2 or anything like that. X can't be inside a radical or even in a denominator. Everything is going to look like some real number constant times x, or x to the 3rd, or x to the 10th. That will be every term of a polynomial. Each monomial is a term that looks something like this, and then the polynomial is the sum or difference of such terms. So I'm going to show you 5 examples right here. Are these polynomials? Let's take a look at them one by one. If I say 2i x squared minus 3x to the 4th plus 11. Again, what makes it a polynomial? Real coefficients and whole powers of my variable. Well, if I look at my variable, x squared, x to the 4th, those are both whole numbers, but if I look at my coefficients, I see 2i. 2i is not real. So this is not a polynomial. What if I said f of x equals negative 0.7 x to the 5th plus pi x minus the square root of 3? Well, if I look at my coefficients here, negative 0.7 is most definitely real. Pi is real. It is irrational. So is the square root of 3. My powers, 5, x means I have a power of 1, so that is also a whole power. So is this a polynomial? Yes. How about our third example? 5 over x squared minus 4x to the 6th plus 2. Again, if I look at those numbers, 5, negative 4, 2, those are all real numbers. If I look at my powers, I may get fooled here because I see x squared and x to the 6th. Those are whole numbers, but this x is in the denominator. 5 over x squared is really the same as 5 times x to the negative 2nd. X cannot be in the denominator because it's really talking about a power which is not a whole. So no, this is not a polynomial. My fourth example, 6x squared plus 4x to the negative 1st plus x to the 1/2. Well, negative 1 and 1/2, neither of those is a whole number. So both of those are a problem. Is this a polynomial? No, because each of those terms, not each of those terms, meets these conditions. The coefficients are all real, but not all the powers are whole numbers. One last example right here, negative 3/4 x cubed minus 10x to the 5th minus 7. Negative 3/4, negative 10, negative 7, certainly all of my coefficients are real. If I look at the powers, I see x cubed, 3 is fine, x to the 5th, 5 is a whole number. I have a constant, which is also fine, so yes, this is most definitely a polynomial. All right, so once we understand what a polynomial is, understanding this idea that we need real coefficients, we need whole powers of x, and we can't incorporate strange things like division by a variable or radicals or absolute values. That is to say, a radical with an x inside. Square root of 3 is fine. Once I understand what a polynomial is, I can talk about classifying them. I can classify a polynomial both by its degree and by the number of terms in that polynomial. So, when I talk about the degree of a polynomial, the degree of a polynomial is the highest degree or power of any of its monomials. So I see some examples right down here. My first example, this is degree 0. f of x equals 2. Why is this degree 0? Well, it's 2x to the 0. As we discussed, anything to the 0 power is 1, so this says 2 times 1, which is just 2. All right, well 2 is just a constant. So this is called a constant function. That's a C. Closed it too much. That's a constant function. What if the degree is 1? Then I see examples such as this, negative 5 halves x minus 3. That is what we'd call a linear polynomial. What if the degree is 2? Then, what have we been talking about recently? This is a quadratic polynomial. Here the degree is 3, 5x cubed plus 10x squared minus 4, that is cubic. Notice something here. I went from having 1 term to 2 terms to 3 terms. This one only has 3 terms, but notice I'm missing an x term. I'm missing a linear term. And this will be common. We'll see a lot of polynomials that won't have every last possible term taken up. If the degree is 4, a 4th degree polynomial, the name is a quartic. Okay, such as this. I can see that highest degree right there is 4. There are some other terms that are missing, but this is a quartic polynomial. If I have a higher degree, such as 5 or 6, there actually is a special name for a 5th degree polynomial, but we're not going to really bother to learn it. A 5th degree polynomial, 6th degree polynomial, that's exactly what we'll say. 5th degree, 6th degree. In general, we could say nth degree. So if I had a degree 10 polynomial, I would just call it an nth degree, a 10th degree polynomial, excuse me. So examples of these might be, I might go very simple and say x to the 5th. For a 6th degree polynomial, I might say something like negative 2x to the 6th plus x cubed minus 10x. That would be an example of a 6th degree polynomial. Alright, so I can classify both using these terms by degree, but I also need to be able to classify by number of terms. These are a bit easier. You've probably heard these already a lot this year. If the degree is 1, if there is 1 term, then that's what we call a monomial. If there are 2 terms, that's what we call a binomial. 3 terms is a trinomial. And any more than that, we don't have a special name for it. They're all polynomials, but if there are 4 or more terms, I just call it a polynomial. There's nothing special to say there. All right, so we have this vocabulary now. We want to use it to classify some polynomials. So if I'm looking down here, I need to look for how many terms there are and the highest degree of any of them. I see 3 terms, and the highest degree is right there. This is a 3rd degree or cubic trinomial. For b down here, g of x equals 7x minus 11. Well, this is my only term of the variable. That's my highest power term. The degree is 1, which makes it a linear binomial. And then c, this looks a little bit grosser. h of x equals 10x minus 5x squared plus x to the 7th minus 2x to the 4th. Again, it's definitely a polynomial. Calling back to what we just said, all the coefficients are real, the powers are all whole numbers. My highest power is right here. I see this is x to the 7th, so I will call this a 7th degree. How many terms are there? There are 4, so no special name, it's just a polynomial. All right. So as I said, this vocabulary is one of the things that you should, hopefully it sounds familiar, but if nothing else, it should be something that you can take away from watching this. The next thing I'm going to talk about is the first bit of math that we can actually discuss with polynomials, and that is end behavior. It's going to turn out that end behavior for polynomials is very, very predictable. It'll depend only on 2 things. If the degree is even, such as a quadratic, quartic, 6th degree, and so on, or if it is odd, linear, cubic, 5th degree, so forth. In addition, we also need to consider the sign of the leading coefficient. The leading coefficient is the coefficient of the highest degree term. It's in the lead when we put the polynomial in what is called descending order. Another term I've used before, descending order, meaning the highest power has to come first. All right. So, if I'm thinking of an odd degree polynomial, for an odd degree polynomial, what I want to think about is y equals x or y equals negative x. Very simple polynomials. Y equals x is a line with a slope of 1. Passing through the origin. Y equals negative x is a line with a slope of negative 1. The first thing I notice is the ends go to different places. Ends go to different places. What I can see, y equals x, as x increases, as x approaches positive infinity, so does y. As x approaches negative infinity, y also approaches negative infinity. If I do y equals negative x, then as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y is approaching negative infinity. Either way, the ends go to different places. One end is up, one end is down. If I have an even degree polynomial, we want to think about y equals x squared or y equals negative x squared. These are some simple polynomials we dealt with lately. We know exactly what they look like. Y equals x squared is a parabola through the origin. Y equals negative x squared is also a parabola through the origin, but with a reflection in the x-axis. So it is opening down. So what do I know here? I can see that the ends both go up or both go down. So both ends go down, or both ends go up, or both ends go down. And it'll turn out that every other polynomial is going to follow this same pattern. So if I have another even degree polynomial, a 4th degree polynomial, the end behavior will follow the same as one of these 2 graphs, depending on if the leading coefficient is positive or negative. Either both ends will go up or both ends will go down. If I have another odd degree polynomial, I can think of something like this. The graph will look about the same. It might have a few more turns or bumps in it, but it'll look somewhat similar, at least as far as end behavior. So in addition to understanding that if it is odd, the ends go in opposite directions, and if it's even, they end up the same way, exactly the same, we also want to notice if the leading coefficient is positive, the graph generally goes up, whether that's going up from left to right or both ends going up. If the leading coefficient is negative, the graph generally goes down. In the case of an odd degree polynomial, it will go down from left to right. In the case of an even degree polynomial, both ends go down. So we want to take these ideas, we want to put this together, and we want to be able to just be given a polynomial and determine its end behavior based only on its degree and whether or not the leading coefficient is positive or negative. So if I'm looking at A right here, again, I want to look at the highest power term, the leading term, which is 4x to the 5th. So my leading coefficient is positive, my degree is odd. So I need to think about when I graph this, it's going to go generally up. Like I said, it might have some turns or something in the middle, but it generally goes up from left to right. As x approaches negative infinity, y must also approach negative infinity. As x approaches positive infinity, y will approach positive infinity itself. Another example. What if I say y equals negative x to the 6th plus 8x to the fifth. The leading coefficient here is negative. The degree is even. So I know if the degree is even, both ends have to go to the same place. If the leading coefficient is negative, the graph generally goes down. So I might see something like this. Again, I don't know exactly what the graph looks like. It might have more bumps, more turns. I don't know. But the end behavior I do know. Both ends have to go down. So as x approaches negative infinity, y will approach negative infinity. And as x approaches positive infinity, y will also approach negative infinity. All right, let's do one more. Y equals 8x minus 2x cubed. So I have to think, again, about my highest power term to get my leading coefficient and my degree. Well, be careful here. The highest power term is over here, negative 2x cubed. So that is a leading negative and an odd degree polynomial. Odd degree means the ends go opposite directions. Negative means it's going to go generally down. So, what result do I have? As x approaches negative infinity, the left side of the graph, for smaller x's, y is approaching positive infinity. As x approaches positive infinity, for larger x's here, I see that y is going down towards negative infinity. Again, it takes some practice, but ultimately, we're looking at two things. The degree, is it even or odd? And then the leading coefficient, is it positive or negative? Those two things allow me to say my graph looks something like this and figure out the end behavior. All right. Hopefully that makes sense. Hopefully that is helpful. If you're still watching, I'm going to keep going and explain end behavior a little bit differently. This is a kind of a concept way of looking at it. So end behavior is asking about what happens for either very large x or very small x. That is, as x approaches positive infinity or as x approaches negative infinity. So you can think about this with actual numbers, 1,000, 10,000, a million, or their negatives. So here's an example. F of x equals negative x to the fifth plus 8x cubed plus 5x minus 1. If I put 10,000 in for x, what do I get? Well, 10,000 to the fifth, 10,000 to the third, just there 10,000. And you can see I've multiplied it out. 10,000 to the fifth means I've got 5 of them. 10,000 to the third, there's 3 of them. And I've written it out with all the zeros. That is negative 100 quintillion is what that number is. Down here I have 8 trillion, 50,000 minus 1. Well, here's something to consider. As many zeros as there are down here, this is still, in terms of its magnitude, is almost 1,000,000 times as large as everything else in this polynomial. So as x gets larger and larger and larger, that x to the fifth term is going to take on more and more significance. As x gets very large or small, the highest power term also gets very large or small compared to all the other terms, to the point that all the other terms lose significance. So if I'm looking at this, if I said f of x equals negative x to the fifth plus 8x cubed plus 5x minus 1, I know that for big x's, all I really need to consider is negative x to the fifth. If I put in something like 10,000, then what am I going to have? I will have negative 10,000 to the fifth, which we know means I'll multiply this out 5 times. I don't really want to rewrite this whole thing a bunch more times. 10,000. I need 2 more. Plus whatever comes next. But as x gets very large, as x gets very large, those terms take on very little significance. And what do I see here? I have a very, very negative number. Okay, negative 1, 0, 0, 0. It's 20 zeros is what it is. So essentially, we are approaching negative infinity. That's what that means. If I put in negative 10,000, then what would I have? I would have negative 10,000 to the fifth, which means I'm taking negative 10,000 5 times. And here's what I have to consider. As I multiply more and more negative numbers together, signs start to change. 1, 2, 3, 4, 5, 6 negatives with the one that was in front means this is going to be positive 1 and then 20 zeros still. So this is why, as x approaches positive infinity, I get a very, very large negative number, very far into the negative. So if x approaches negative infinity, well, because of the way the signs are going to multiply out, I will get a very, very positive number. So that's where I can see approaching positive infinity and approaching negative infinity. Sorry, I'm a little bit below the screen. Approaching negative infinity. If I did this with an even power, then what would I have? Well, if I put in, I'm going to use 1,000 just to save myself some zeros. I know I can focus only on that first term. When x equals 1,000, I will have 3 times 1,000 to the fourth minus all the other stuff which loses significance for large x's. Well, if I raise 1,000 to the fourth, I'm going to get a whole bunch of zeros. Specifically, I'll get 12, it looks like. But what's happening to this? Again, I get a large positive number, so I can see where it's approaching positive infinity. If I think about when x approaches negative 1,000, or excuse me, when x equals negative 1,000, again, what happens is I take powers of negative numbers. Well, 2 negatives make a positive, 2 more negatives make a positive. This will again be 3 followed by, it looks like, 12 zeros. $3 trillion. So again, I can see, in agreement with what we said, since this is an even degree polynomial, both ends go in the same direction, and since the leading coefficient is positive, both ends, as x gets very large and as x gets very small, are tending towards infinity. So that's just another way of looking at end behavior, the actual idea behind it, the actual math behind it. Hopefully that makes some sense. Either way, study hard, work hard,